Good morning, afternoon, or evening, whatever time it is for you watching this, and welcome to Magnetism Notes Part 1. I'm going to go through the first half of the slides here. So let's kick things off with some properties of a magnet. First thing to know, which you probably already do, is that a magnet has polarity. It's got a north pole and a south pole. What would happen if you were to cut this magnet in half? It would actually make two smaller magnets. You would have two north-south magnets. You wouldn't ever have just a south pole or just a north pole. You would have two different smaller magnets. Like with electric charges, like poles repel, opposite poles attract. So north and south are attracted to each other, north and north would repel each other. If you've ever played with magnets before, you felt this when you try to put like magnets next to each other and they repel and push apart from each other. And you might have noticed if you ever held an actual physical compass with a suspended magnet in it, that it actually points to geographic south. But I know when I hold a compass that it points north. That's how I find my way out of the woods when I'm lost. Compasses point north. So what's going on? It is a weird thing about Earth that right now, the North Pole, physically, where Santa lives in the Northern Hemisphere, is actually the magnetic South Pole of Earth's magnetic field. Right now, Earth is kind of flipped upside down, its magnetic field. It flips back and forth every couple 100,000 years. But right now, we've got geographic north. The North Pole is magnetic south, and geographic south is magnetic north. So your compass is pointing to magnetic south because it is the north part of the compass in your hand is pointing to magnetic south, which happens to be geographic north. Magnets can only be made of certain materials. Only certain things can become magnetized. Iron, cobalt, and nickel are common materials that could become magnetized. They are all ferromagnetic. They are also rare earth metals, but ferromagnetic is the name of the property that these materials all have. That means they can become magnetized. It was Ørsted who discovered that moving electric charges can create magnetic fields. So his compass was being deflected by a moving charge, a current here, and he realized that there's some kind of connection here between electric charges that are moving and magnetic fields. So where does magnetism come from? How do I end up with something that's magnetized? It's all about these moving electric charges. The spin of electrons in atoms creates what's called a magnetic domain. And if the magnetic domains are all lined up, then you have a magnetic material. So here I've got these domains that are all pointing in the same direction. That tells me that this nail has become magnetized. Up on the top, those magnetic domains are pointing in all different directions, so this is not magnetized. There are a couple different ways you can ruin a magnet. Anything that would randomize the alignment of those domains. So if those arrows end up pointing all over the place again, you don't have a magnet anymore. So if you were to drop the material and it gets shaken up and all of those arrows are pointing different ways, the domains are randomized, it's not a magnet anymore. If you were to heat it to a certain temperature, it would lose its magnetic properties. There is a property of a material called the Curie temperature, which is the temperature above which the material loses all magnetic properties. So once your magnet reaches its Curie temperature, it's not a magnet anymore. Or if you expose the magnet to another magnetic field, it's no good. The alignment of the domains becomes out of whack. VHS and cassette tapes record sound and video by aligning magnetic material on the tape, which is why if you've ever dropped a VHS or a cassette tape before, if you have any of them, you've got to cross your fingers that you can still watch that movie. You can create a temporary magnet in two different ways. First is by putting an object made of a ferromagnetic substance into a larger magnetic field and aligning the domains. Second is by running a current through a coil of wire to create an electromagnet. And we're going to talk more about electromagnets later. Like how electric charges create electric fields, which have electric field lines, magnetic fields have magnetic field lines. They are drawn as loops that point from north to south. So we've always got these loops that are coming out of the North Pole, pointing into the South Pole. How would I draw the field lines for Earth? Well, remember, geographic north is magnetic south. So even though this says north, that is magnetic north, which is in geographic south. So if I were able to flip this picture upside down, the magnetic field lines would come from the geographic south pole, which is magnetic north, loop around and point up into geographic north, which is magnetic south. So it's this picture upside down. Now, what if I had this little drawing of a compass where the shaded part of it is north? I want to move this little compass to the right of this magnetic field. What way should I point it so that it lines up correctly? And there it is. Next, we've got the magnetic force. Magnetic fields can cause a force on an object, specifically charges that are moving through it. The B field is referring to the magnetic field. M has already been taken by mass, so B is what we use to refer to magnetic fields. A charge will feel the greatest force when it is moving perpendicular to the B field. Charges feel no force if they move parallel to the B field or to the magnetic field. If the charge is moving along a magnetic field line, it will not feel any force at all. If it is moving across the field lines, it will feel something. When they are exactly perpendicular, that is when you will have the greatest force. If it's at a smaller angle, the force will be a little bit less. Perpendicular is when you have the greatest force, and we're going to assume that they're perpendicular most of the time. But if it was not perpendicular, then it would be a smaller force. So the magnetic force felt by a point charge is shown with this equation. Two magnets are applying a force on each other. So if I have a moving charge, which remember, moving charges make magnetic fields. So I've got a moving charge, which has its own magnetic field, moving through a different magnetic field, it will cause a force. So here I have the force, the little m means magnetic. So the magnetic force is equal to the charge times the velocity times the magnetic field, B. So your charge should be in coulombs, your velocity in meters per second, and your magnetic field we typically measure in a unit called the Tesla. So this B is referring to the magnetic field, the unit is Tesla. So here's a sample problem. We have an electron beam that is experiencing a downward force of 2 times 10 to the negative 14th newtons that's traveling in a magnetic field of 8.3 times 10 to the negative 3 Tesla directed to the west. Find the magnitude of the velocity of the electron. So I've got my force here is 2 times 10 to the negative 14th. I have my magnetic field is 8.3 times 10 to the negative 3. It tells me it's an electron, so I know that my charge, Q, is equal to the elementary charge, the charge of an electron, which is 1.6 times 10 to the negative 19 coulomb. I've got my equation is F equals QVB. So I plug in the things that I know, and I need to solve for V here. This question only asks about the magnitude, but I want to take a second to think about the direction also. You might notice on the note sheet there's something about the right hand rule all the way at the end. Just to make it extra confusing for you, I'm going to tell you there are two different right hand rules. And I'm going to explain the first one now. We've said that a electron beam or a moving charge feels the most force when it is moving perpendicular. So I'm going to draw a little picture here. It told me the electron beam experienced a force that is moving down. So there's my force going down. In a magnetic field that is traveling to the west. So I've got a magnetic field moving to the west. I'm assuming that the electron or the electron beam is perpendicular to the magnetic field. Most of the time, the question will say an electron beam traveling perpendicular or at a right angle to a field. Most of the time, it will specify that. If it doesn't, then you can assume it to be true. So I've got this beam that is pointing to the west. I've got a force that ends up going down. The force is also perpendicular to the field. The force is also perpendicular to the electron beam. Before, for the most part, we've been working in two dimensions. When we had a projectile, it would move up and then down and to the side, all the while moving in the y-axis and the x-axis as it made an arc. Now that we've got things that are perpendicular in three directions, we are working in three dimensions. If you were to draw a graph, it would look something like this, and this is not a very good graph, I'm sorry. But you can imagine we've got an X and a Y plane, the way we're used to seeing it, and then we've got a Z plane additionally, where that is coming out of or going into the screen. So when you've got a magnetic force, we have to work in three dimensions. So the first right-hand rule looks something like this. Some people will also just hold a flat palm. For me, it was always more helpful to point with one finger. But before I explain how to use this, I'm going to explain why I'm using it. I know that all three things have to be perpendicular to each other. So when I hold my hand like this, I've got my thumb pointing in one direction, perpendicular to it. I've got my finger pointing up, perpendicular to both of them. I have another finger pointing straight out. Another way you can see it is with a flat palm. I've got my thumb pointing to the left, I've got my fingers pointing up, and my palm is pointing out in another direction. Either one of those works for this. I preferred this one personally. But I know that the electron is going to feel the most force when it is perpendicular to the magnetic field. So here's my magnetic field going up. My thumb pointing to the left is perpendicular to that. The force is perpendicular to both of them. So if I hold it up this way, I've got the force is perpendicular to my thumb, and I can see the force is perpendicular to the magnetic field. So here I've got velocity, magnetic field, and force, or if you do it this way, velocity, magnetic field, and my palm would show the direction of the force. But now I've got all three are always perpendicular to each other. Excuse me. And now I can figure out which direction the velocity is going. Because remember, even though here it only asks for magnitude, velocity is a vector, which means it has a direction as well. So I'm going to take my weird three fingers pointing out. I said my middle finger was force. That has to go down. I can already kind of see B, my magnetic field, was my pointer finger. And now you can't see it because it's hidden behind my hand, but that means my thumb is pointing into me, or here it would be out of the page. So I can arrange my hand to see what direction whichever vector I'm missing has to be traveling in. So play around with this or with the flat palm version. If I do it that way, I've got the palm pointing down because of the force. I've got B pointing to the left or westward for the field. And again, my thumb is coming out of the page. And that is the first right hand rule. Coming up in just a little bit will be the second set of notes continuing on.